now this is recording. RTI
International
Center for
Forensic
Science
presents
Just Science.
Welcome to Just Science, a podcast for forensic science professionals and anyone who is interested in learning more about how real crime laboratories work. In episode 9 of Just Science, we interview Marc Smith from the Georgia Institute of Technology about his NIJ-funded research in blood spatter. Marc has connected computational fluid dynamics with empirical studies to improve the understanding of blood spatter onto solid, slanted surfaces. The work looks at many variables, including droplet size, speed, surface roughness, and wettability. Funding for this episode is brought to you by the National Institute of Justice's Forensic Technology Center of Excellence. Here's your host, Dr. John Morgan.
Welcome to Just Science. This is part of our series from the meeting in New Orleans of the American Academy of Forensic Science. We're talking with various folks who presented at the NIJ Research Symposium earlier in the week. And here in pleasant New Orleans, in the middle of February, this is the time to be in New Orleans. The NBA championship is this weekend. Mardi Gras is about to hit full steam, and it's a happening town. And of course, the most important thing going on is the American Academy of Forensic Science meeting and all the great research that NIJ has funded that you can learn about here. We're going to talk today with Marc Smith from Georgia Tech. He's going to be talking about blood-stain pattern evidence, which is an interesting topic and not one that NIJ has put a lot of research dollars into. And I want to explore kind of broadly blood-stain pattern evidence and talk about Marc's work in particular. Welcome to the podcast, Marc.
Well, thank you very much, John.
How long have you been at Georgia Tech?
I arrived there in about 1991, so 26 years about now.
Okay.
So it's been a while.
You came from Johns Hopkins University in the engineering school before Georgia Tech, is that right? Yeah.
Yep.
So what did you do in Mechie back at Hopkins, and have you been doing Mechie work entirely at Georgia Tech, or how'd that work?
I was on the faculty in mechanical engineering. I went to mechanical engineering at Georgia Tech. It was all fluid mechanics type basic research. My background is a lot in hydrodynamic stability, so I was doing theoretical calculations, liquid films and liquid droplets, and things of that type.
Which leads directly into blood, really, doesn't it, I guess?
Exactly.
Blood is just, from your perspective, just another interesting fluid.
Yeah, very interesting fluid.
So what led you to want to work in forensic science and bloodstain pattern?
It was a number of years ago, probably about 4 years ago, and I had a colleague, Paul Neitzel at Georgia Tech, who served on one of the proposal review panels for NIJ. And he heard about extra research dollars going into funding to put forensic science on a little bit more basic science level. Mm-hmm. And, he got interested in what blood spatter was doing and what that was like. And we thought that it would be a great opportunity for us to get into this field. It's a basic fluid mechanics topic, yet a very complex fluid, and the application of it is quite difficult.
Sure. Are you looking specifically at how fluids flow is kind of where your specialty is, or how does that work?
My basic interests are when fluids flow, particularly fluids with interfaces. So this could be a thin liquid film or a droplet that has an interface with air, for instance. Those interfaces can undergo instabilities as they move. Mm-hmm. And so you can apply some mathematical theory to that problem and come up with criteria for when those things will become unstable, when the interface changes from, say, a nice planar interface for a film to one with waves on it. And so we're looking at the theory behind that, trying to predict when this would occur. For blood droplets, or just droplets in particular, they have a very specific mechanism for spreading out on a solid surface when they hit that. And there are some instabilities as well associated with that spreading. So you'd like to be able to characterize them completely with all of the theory that we have at our disposal in fluid mechanics and apply it then to this problem.
From the perspective of bloodstain pattern analysis itself, so I look at it as a problem that really doesn't need solving. Isn't it just a bunch of physics and parabolas and projectiles and things of that nature? Where do you see the weaknesses with respect to how we look at bloodstain pattern analysis in particular?
The techniques that are being used right now are certainly very effective, and they're used all over by practitioners in the field. But what we're trying to do is look at some of the basic assumptions involved with those techniques and analyze them a little bit better, get some better data, and try to come up with some bounds on the accuracy that you can expect. So for instance, in bloodstain pattern analysis, One of the things that are done is you look at a large number of the droplets that hit in a surface. From the impact, track out the trajectories of those particles and try to find out where they converge, or those trajectories converge. And to do that, you need to know what the impact angle of each of those blood droplets was on the surface. Also be nice to know the size of the droplet and the velocity that you would have, the impact speed. Right now, you look at the shape of the droplet as it hits the surface. Typically looks like an ellipse, unless it's a perfectly normal impact, then it's
Perfectly perpendicular.
perpendicular, normal, yeah. So when it's inclined to the surface, the blood droplet spreads out a little bit more in one direction than the other, so it has an elliptical shape. And you can measure the different width and the length of the droplet. And right now there is a very simple relationship that maps that ratio of width to length back to an impact angle. So one of the things that we were looking at was just trying to figure out how good that actually is. And so we did some measurements on a wide variety of droplets hitting a surface at a lot of different impact angles, and then tried to basically just plot our results and see how good that kind of a prediction would be.
So what variables are you looking at? I assume you're looking at the size of the droplet, right? Its velocity, its angle. Is there much variation in blood with respect to its viscosity and its properties as a fluid itself?
Yes, it can be, and it's a very complex fluid. It's not a simple fluid like water. It's got red blood cells and all sorts of other things in it. So it's what's known as a non-Newtonian fluid, and that complicates things a lot. And then just between different people, the blood viscosity can vary. And all of these things impact kind of the measurements that are made, or the practice that's done with these blood droplets to do the forensic problem.
So the research work that you're doing really is on the impact itself.
Correct.
So you're looking at the impact spot, basically.
Right.
The predictive analysis is really, what you're trying to do is back out. So to what extent can you look at a spot and actually match up with very specifics in something as difficult as the viscosity of the blood?
This is really the problem with it. I mean, in a real crime scene, you have so many variables, like the surface itself could be different roughnesses, even porosities, different types of surfaces from paper to glass. Like you said, the viscosity can be different between different people, and the blood droplet itself is non-Newtonian fluid. So what we're doing is trying to look in as simple a case as we can to try to get a baseline for well-defined fluid with a well-defined surface. When we do our measurements of a droplet impact on that surface and basically create that kind of a spot, can we then back out all of these parameters that we're trying to determine, like the speed, the impact angle, and the droplet diameter? How accurate and reliable can we do, just even in the simplest case? And that then would allow us from there to start looking at more complexities. Which I should mention here as well, that the fluid that we're looking at is not blood. We made a blood simulant, which is a very Newtonian fluid. It's basically water and glycerin, a little bit of alcohol, that matches the properties of blood. But still, it's a very simple Newtonian fluid. So if we can get good, accurate relationships based on just that simple fluid, then as we add the more complexities of real blood or rougher surfaces or porosities in the surfaces, we can then back out just what kinds of accuracy we can expect on the relationships that would be involved.
The complications with blood itself are that its viscosity varies, but it's also basically, it's almost like a colloid, right? Is that why it's non-Newtonian?
That's right.
It's basically full of particles that adhere to one another.
Right, red blood cells that can change their shape, other particles, blood platelets and so on, that are in there that basically just change the properties of the fluid itself.
At this point, though, your model is a Newtonian fluid. It's a model of blood. Are you varying viscosity across or not?
No, we're using the blood simulant just basically fix the properties. What aids us in this case is there are dimensionless groups that are appropriate for this kind of a problem. There's a Reynolds number and a Weber number that basically characterize this droplet impact problem. Like the Reynolds number is a ratio of inertial forces to viscous forces, and the Weber number is inertial forces over surface tension forces. So it's a ratio of these two effects. And when you vary just that parameter, then you're getting the full effect of the variations on the physics that you're looking at. And so the viscosity is one of the physical parameters that appears in the Reynolds number, but there are velocity and diameter. And so we change velocity and diameter and effectively then change the Reynolds number. So we don't need to actually go in and change, use a bunch of different fluids, which makes things much more complicated than they actually need to be. We can just change a few parameters and get a full range of variations of the Reynolds number.
Is that approach to how you look at blood droplets reflected in current practice in blood stain pattern analysis? Do they actually try to derive a Reynolds number of a particular droplet or not?
I have seen it both ways. I mean, there is certainly some work where that's the approach. And that's a standard approach that people who, basically breathe fluid mechanics, that's the way they think. They think of dimensionless groups, and that's how they put the data and characterize the data. There are other correlations that I've seen that basically assume that there's a standard viscosity, and then they just have a correlation among just the physical parameters like diameter and velocity, and that's the correlation they use. That's certainly simpler because you just have a couple of things to worry about, but it ends up missing a lot of things like the effect of viscosity. You wouldn't be able to really see that. You're just looking at a correlation that is for blood, so it matches size and speed and that kind of thing, but you can't really go anywhere else with that.
Is the generation of these droplets at particular controlled Reynolds numbers and speeds something that is relatively easy? Is that something that a fluid dynamicist already knows how to do, or did you have to develop that for this research?
Well, we developed a device that would generate droplets, but I could say it's unique to our research, but it's certainly not the only way to create single droplets. There's a ton of people that do this kind of thing, and you've probably used devices that does this as well. Just an inkjet printer is exactly the same kind of thing. They have a device in there that creates single droplets of ink on demand and propel it against the paper. So we just took some of those ideas and put it into a system where we could use that to generate our droplets. We wanted things that were a little bit bigger.
Right, of course.
We got up to about droplet sizes of about 5 millimeters or so. And those particular devices, that's micron size. We actually do want to get to that size and look at some droplets that are not only that size, but also much faster than we can do. But for this first experiment and the first research that we did, we developed a generator to create a single droplet on demand. We had a range of diameters and speeds that we could do, and that's what we worked with for this first case. Right.
So what surfaces are you looking at?
Well, we did 3 surfaces. We did a glass surface, a bathroom tile, and then just a paper surface. And thinking that these were kind of representative of what you would see in a crime scene. Certainly not all the surfaces that would be there, but it was a start to look at. We were also interested in just the range of roughnesses that you would get in these surfaces. So glass is very smooth. The tile was ceramic tile. It had lots of different patterns of roughness in it.
Sure.
And then the paper was the roughest yet. And that was also a little bit porous. It would absorb some of the simulant that we threw on it. So that was what we started with. We've decided, looking at that result, that we need to do a much more careful investigation of the roughness element in the surface, because that has a big effect on the results that we saw.
Even small variations in the surface will change the wetting parameter, the ability of the blood simulant or the blood to spread across that surface and how it's going to spread.
Right.
And that's a very difficult thing. There's no way anyone would have a basis for doing that kind of analysis without having a lot more science done than what we've done so far.
This spreading properties that you're just talking about even is more than just the roughness elements that we're talking about. You can have a perfectly smooth surface, and the contact angle of any droplet, any fluid on that surface can vary from being very hydrophobic to hydrophilic to wanting to spread out on the surface. All of that impacts the spread of the droplet that you would see on the surface, even though it's completely smooth. So that is an effect that we need to be looking at as well. At least we're lucky that it is blood, and so it's kind of the same kind of fluid, and we're not looking at a range of fluids that could wet the surface very differently. But just that effect is something that we did not really put in any effort at looking at this point. We're just throwing our simulant on the surface and seeing what happens. That would be a parameter that we would like to investigate in the future.
So you've looked at these 3 different surfaces, at least from a reasonable perspective, and I assume to some level you can model within some error what to expect. Is that something that you feel confident in at this point, or where are you in your research?
We have been able to fairly reliably predict. There's a standard practice relation that I mentioned before. I'll get a little technical here. So we call this parameter, which is the droplet width over its length, the stain. Bloodstain parameter, the aspect ratio. And if alpha is the impact angle measured with respect to the surface, then the sine of that angle, sine of alpha, is equal to the aspect ratio. That very simple relationship has been around since the late 1800s and used as standard practice to investigate or to look at an elliptical bloodstain and map it back to its trajectory, its impact angle. It's a very simple relationship that just fits data at this point. We found that as the impact angle becomes more shallow, as it becomes closer to, say, 40 degrees with respect to the surface, this relationship has a bit of error associated with it. And you would, I believe, over-predict what the angle would be if you use that standard relationship. So our work now has been able to extend that down to shallower angles so that we have a better relationship. And based on that work, it looks like we've got about a 10% accuracy in terms of the prediction of the theory of the correlation that we have versus the standard practice. So that's the kind of thing that we're trying to get a little bit better handle on, is if you have these relationships that you can use in the practice, in the field, what is the accuracy limits that you can have? How good is it? And very carefully, well-defined experiments would answer that question.
So I'm assuming that's mostly a viscosity effect. Basically, as it gets gooier, it's going to spread out less than you might expect from the simple geometric analysis, or is that too simplistic?
It's not just a viscosity effect. As the droplets become faster, that effect that you're talking about is going to be mitigated a little bit. Faster droplets have more inertia associated with them, and so they're going to spread a different way. If they're slower at the same viscosity basically starts taking over and they spread differently. So it's not just a viscosity effect. This is where the Reynolds number comes in.
Right, of course.
And so as you vary that parameter, you can have a whole range of different effects, from basically viscously dominated spreading to one that's dominated by surface tension. And these are the things that you have to kind of balance when you're looking at this work. All of the different parameter ranges that you could see lead to different effects and different behaviors.
So is it the case then that glass was the one where the effects associated with Reynolds number were most predictive because it is the simplest surface, as opposed to paper where the surface might have had more of an...
I wouldn't say it was the fact that the work was associated with just the viscosity of the fluid in these different surfaces. Yeah. It's true that when we had a glass surface, we had the least amount of variation in our data. It was smoother. I mean, we took pains to clean the surface and fire clean the surface, basically. You need to do a lot of stuff to make sure it is in a pristine condition. And so that when the droplet spread, it would spread out pretty much the same every time. And when we did those experiments, the variation that we had, the scatter in the data, was minimized, which is kind of what we expect. On the other side, paper, that was much rougher than glass. It was even rougher in different directions than we expected. Well, not expected, we measured it, so we knew we knew what the variation was going to be. But that roughness changed the way the droplet actually spread, not just due to the viscous effects, but due to the travel of the contact line along the surface. A little bit of absorption into the material itself caused difficulties. And so all of those effects basically change the spreading process every single time. It's like every droplet hitting the paper surface looked different than the one before it, even though the Reynolds number was precisely the same. And so there was a lot of variability in the data just from that particular surface. And this is one of the things that we would like to get a handle on, because we can control the surface in the lab, but in the field, you're not going to be able to do that. At the best, you can sample the surface and say, this is the kind of roughness that we saw. And if we did a good job in terms of the experiments and the theory that we're looking at, to say, for that kind of roughness, you would expect to see this kind of behavior within this kind of accuracy, then that's information that they could use. And that's where we want to really go on this. Not just give them a correlation, but give basically support to the quality of that type of correlation or theory that they would use to reconstruct.
Yeah, I mean, that is, I think, what the field is looking for right now. I mean, is the idea of, this is what I've observed. These are tools that I'm using. To what extent am I able to come back and say, yeah, this has a scientific basis?
Right.
And we accept that there's going to be error associated with it. Bloodstain pattern analysis in particular is interesting from the perspective that it can withstand such error more than others because it's really talking to things around the crime, right? I mean, if your models are able to back up a particular theory about where the blood came from, right, you can ground that in other fact patterns. But on the other hand, even just to the extent that you've gone so far, there is an enormous amount of complexity. On the surface, as I was saying, if you excuse the pun, sounds like a straightforward problem, but it really is. There really is an awful lot of variation to it.
There really is, and that is essentially is our goal now, is to try to tease apart that complexity that you see, put some numbers on it in terms of the accuracy that you'd expect, and give it back to the practitioners who could use it in the field to do a crime scene analysis, who could go in a court and basically make statements based on some solid experiments and have some good accuracy results behind it that can make statements about what the results say.
So it does sound like there's definitely more work to be done. Where are you hoping to take the work from here?
We've got lots of avenues that we can follow, but one of the ones that we are interested in our work in the past, we were kind of limited in our Reynolds number range and Weber number range to, let's say, Reynolds numbers up to 4,000 or 5,000, which is large, but not particularly large. And this particular range of Reynolds number would be appropriate to things like dripping blood on a surface, or if you get hit by a blunt force trauma and there's a bloodletting event. Those are the kinds of Reynolds numbers that you'd expect to see in those situations. Another situation is just a gunshot wound, which you get Reynolds numbers on the order of, say, 80,000 or so. We can't access that range of Reynolds numbers with the equipment that we have at this point. So we would like to come up with a way to generate not only faster droplets, we need to get about 100 meters a second in terms of getting up to the right speeds. We also would like to get to smaller droplets on the order of 10 microns or so, or 100 microns. This is the parameter range of interest when you're looking at gunshot problems. And right now we can't really make any statements based on that because we can't access that range of parameters. So one avenue that we're looking at is to go into that field. The other avenue is we certainly saw that surface roughness is a problem. Not a problem, it's a very characteristic feature of these types of problems. We'd like to set up a set of experiments that are really well-defined roughness, kind of uniform at this point across the surface so that it doesn't have any surface variation that way. But something that we can quantify very well from smooth as glass that we have now up to something as rough as paper that we have now. But just make them very well defined and categorized. And then repeat the experiments based on that. What we found is that this effect certainly is important in the spreading problem. And so if we can get a better understanding or characterization of that effect, then the theories and the correlations that we come up with will be able to be that much more appropriate to the field.
So within the bounds of what you have been able to do, within 4,000 or 5,000 Reynolds number and so on, do you feel comfortable with respect to its maturity, with respect to it being used in practice? I mean, how do you feel it would be appropriate in that regard to try to adopt it in the bloodstain pattern field right now?
I think our first contribution, which was to look at the standard practice relationship and show the deviation that we see with respect to that relation for the shallower angles, I think that's appropriate at this point. That seemed very robust. It was persisted across all different kinds of surfaces, and that we were able to show seemed to be accurate to within about 10%. So we have a correlation that fits a little bit better than just the standard practice relation. That would be, I think, ready to go, and we'll be publishing that soon.
Oh, you will be publishing that soon? That'll be something that will be available?
Yeah, that will come out. The other aspect of it, where we're trying to get a couple of other parameters that we could use to predict impact speeds and diameters, that has got a lot of problems associated with it. We're finding a lot of scatter in the data that makes basically looking and fitting the data to any type of a model very difficult. So we're trying to figure out exactly what is causing this variability. And one of the aspects could have been the surface roughness, though I'm not so sure that that is the cause of the variability we see. Another factor, which I think might be more appropriate, is droplets, when they are let fly, let's say, and they start moving, will oscillate a little bit. Certainly when they're generated, they're going to start oscillating. I think that oscillatory effect changes the shape of the droplet as it impacts the surface. And that could change the way it spreads.
Yeah, especially droplets of this size, it could be quite complex.
Right. That's something we had no control of at all. I mean, we generated the droplets. We knew they were oscillating. If you waited long enough, they would stop. The viscosity would just stop them and they'd become spherical and they'd hit the surface. But we couldn't always wait that long. It would have been too big experiment for us to deal with. So there are a couple of ways to do this. Either, like I was mentioning before, just create smaller droplets. Smaller droplets, the effects of viscosity will damp out and they'll become spherical right away. That would get rid of that effect, and we could see what kind of variability is then inherent in the data. The other one is if we've got, and this would be just typical of a larger droplet, millimeter to 3 or 4 millimeters in size, they're going to oscillate anyway. So if you can control that oscillation in some way, so that when they hit, they're always in the same phase of the oscillation, then you've eliminated at least one aspect of that variability that you would see in the oscillation. Then that would give us a way to kind of map any variability we would see as a function of this oscillation parameter that we'd expect. That would be interesting, because then we could say, all right, in a real system, you're going to have this kind of variability just due to the blood droplet sizes and oscillation effects. You will not be able to do any better than this kind of percentage in any prediction that you'd make. And that is information that people would be needing to use in the forensic applications.
Well, Mark, thank you very much for being a part of the podcast. It's been a fascinating discussion on a topic that is very, very important to forensic science. I think we'll find that an awful lot of folks in the forensic science community are very keen to know more about bloodstain pattern analysis and how it can improve it and improve the scientific basis for it, and we appreciate the work you've done in that area.
All right, well, thank you very much for the invitation.
Opinions or points of views expressed in this podcast represent a consensus of the authors and do not necessarily represent the official position or policies of its funding. Next week on Just Science, we will be speaking with Gwyneth Gordon from Arizona State University on her research with isotopic taphonomy of human hair. Please visit the FTCOE's website at forensiccoe.org to learn more about this episode and to watch the 2017 NIJ R&D Symposium webinar that was recorded at the 2017 AFS Annual Scientific Meeting.